Hello everybody, what's going on? Welcome to Unveiling Astronomy Podcast. Today, unveiling the secrets of space. Parallax measurements introduction. Now, this actually gets pretty in-depth. We're just going to go straight into it. Parallax measurement is you know what? This is just an introduction. This will give you a good base. And I'm do a longer. If this is something you're interested in, I'm going to do a longer. There's a longer episode that I do, and you can check that out. Become a patron, and you can hear all my in-depth podcasts. I'm sorry. God, it's one of those days I cannot think at all. Man, so, the title of today, Unveiling the Secrets of Space. Parallax Measurements Introduction. Welcome to Unveiling Astronomy Podcast, where we explore the wonders of the cosmos. In today's episode, we embark on a journey into the depths of space and unravel the method behind measuring the incredible distances to stars, planets, and other celestial bodies. Welcome to the fascinating world of parallax measurements. Understanding parallax measurements. Before we dive into the specifics of parallax measurements, let's grasp the basic concept behind the method. Parallax is a measure of the apparent shift in the position of an object when viewed from different locations. Just as our perception of nearby objects shifts when we change our viewing angle, we can apply this principle to the heavens above. The explanation of parallax. Now, to visualize parallax, let's consider an example. Hold your finger at arm's length and focus on it using only one eye. Now shift to the other eye and notice how your finger appears to shift in position relative to the background. This perceived shift is due to the parallax effect. Now, the application to space. Now imagine applying this principle to objects that are millions or even billions of kilometers away. Astronomers use parallax measurements to gauge the distances of stars, planets, and many other celestial bodies in space. Now, the parallax formula is how can we calculate astronomical distance using parallax? Let's break it down. Parallax angle. The first step is to measure the parallax angle. This angle represents the shift between two different observations of the same object, taken from opposite sides of Earth's orbit around the Sun. Triangulation. By utilizing a technique known as triangulation, astronomers use Earth's orbital distance as a baseline, and the parallax angle to form a triangle with the observed star or planet as the vertex. This becomes the basis for calculating the distance. Now, the parallax formula. The parallax formula, which connects various components, helps us determine the distance to the celestial object. It is as follows. Distance in parsecs equals 1 parallax angle in arc seconds. Practical applications. Parallax measurements have revolutionized our understanding of the universe and have been instrumental in several astronomical breakthroughs. Let's explore a few practical applications. Stellar distances is one. Initially employed to determine stellar distances within our own Milky Way galaxy, parallax measurements helped astronomers build the cosmic distance ladder, aiding in estimating the scale and the age of the universe. Now, the next one are exoplanets. Now, with the advent of powerful telescopes, parallax measurements have been crucial in the discovery and characterization of exoplanets. They allow scientists to understand the composition, orbit, and potentially the habitability of these distant worlds. Now, the limitations and the advancements, these go back and forth. But while parallax measurements have revolutionized our grasp of the cosmos, it's essential to acknowledge their limitations and the advancements that have improved their accuracy. Limitations, one significant limitation is the maximum distance we can measure using parallax. With the most advanced technology available today, we can detect parallax for stars up to a few thousand light years away. Now, the advancements in spacecraft. To overcome this limitation, space-based observatories like Hubble and Gaia have been invaluable. Invaluable is all hell, actually. Free from the Earth's atmosphere and closer to space-based objects, these platforms provide more precise parallax measurements. Now, and a little bit more of an explanation of how parallax measurements are used to measure stars, planets, and other celestial bodies in space and Earth are followed by these step-by-step instructions. I'm going to go over them with you. It's pretty cool, man, really. Start with the basic concept of parallax. Parallax is the apparent shift in the position of an object when viewed from different locations. In this case of measuring celestial bodies, we use the Earth's orbit around the Sun to observe this effect over a period of 6 months. Now, we begin by explaining the baseline. The baseline for parallax measurements is the distance between 2 points from where the object is observed. In this case, the 2 points are Earth's extreme positions in its orbit, which are approximately 186 million miles apart. Now, with discussing the celestial bodies being measured, this explains a distance to the celestial body that is much greater than the baseline. Stars, planets, and other celestial bodies are typically located at distances ranging from a few light years to billions of light years away. Now, when we introduce the idea of angular shift, we're observing the celestial body from one point in Earth's orbit and then observing it again 6 months later from the opposite side of Earth's orbit. The object will appear to shift its position against the more distant background stars. This is the parallax angle, or the angular shift. Now, with this, we explain the calculation. The parallax angle can be used to calculate the distance to celestial body using simple trigonometry. What is ever simple about trigonometry? Just kidding. The smaller the parallax angle, the greater the distance to the object. So, using your finger and putting that, it's a great example. And closing one eye. Now with that, the closer you have it, the bigger the triangle, so the closer it is. So astronomers use a unit called, the parallax angle can be used to calculate the distance to the celestial body using simple trigonometry. The smaller the parallax angle, the greater the distance to the object. Astronomers use a unit called parsec, which is the distance at which an object has a parallax angle of 1 arc second, 1/3 600 of a degree. That's a whole lot. Lincoln, is that not a whole lot, man? Go get him, Lincoln. Now, to provide you with an example, I guess the best example to illustrate for this process would be explain like if a star has a parallax angle of 1 arc second, it is 1 parsec away. A star with a parallax angle of 0.5 arc seconds would be 2 parsecs away, and so on. Now the highlighted limitations. It is important to note the limitations of parallax measurements. For objects beyond a certain distance, the parallax angles become too small to measure accurately. As a result, alternative methods such as using standard candles or spectroscopic measurements are employed to estimate distances to farther celestial objects. So, to summarize the concept, to conclude by summarizing that observing parallax provides astronomers with a valuable tool to measure the distances to nearby stars, planets, and other celestial bodies. It all allows them to create a three-dimensional map of the universe and understand the scale of the cosmos. Remember, to provide additional information that would be, I don't know, kind of like your, the way that the moon is calculated from Earth. It's the same using the Earth, the moon, and then the telescopes. It's pretty crazy, actually. But it's pretty neat. I mean, really. Yeah. And man, really, there you have it. That's the method behind behind measuring the distance of stars, planets, and other celestial bodies throughout parallax. Join us next time as we continue exploring the wonders of the universe. Until then, keep gazing at the stars, my friends. I'm going to take a short break. I will be right back. Don't go anywhere. If you become a Patreon or in my fan base, I do way more descriptions of these of my live podcast. But if you're not going nowhere, I will be right back, everybody. Yeah, as a word to my wonderful sponsors.
Good at short distances where we see quarks moving around, but at long distances, a better description, which, by the way, we haven't yet completely found, is these flux tubes, we say, or fat string. That led to string theory. String theory came from experiment, but not experimental gravity or unified, but rather strong nuclear particles. So, again, we'll perhaps shortly get to. We talk about particles, we talk about strings, but sometimes they're really the same thing.
Yeah, we will definitely get to it.
Different ways of looking at the same physics, and that in attempts to then push that farther, consistently mathematically constructed rigorous theory of the extended object, it turned out that one of the extended objects, a closed ring,
Black holes are the most mind-blowing things in the universe.
They could swallow a star completely intact. Black holes have these powerful jets that just spew matter out. First discovered on paper, on the back of an envelope, some squiggles of a pen. A bizarre solution to a seemingly unsolvable equation, a mathematical enigma. Einstein himself did not accept this as real.
People didn't even believe for many years that they existed.
Nature doesn't work. Yet slowly, as scientists investigate black holes, by observing the effect they have on their surroundings, evidence begins to mount.
That is the proof of a black hole.
Millions of times the mass of the sun.
Cutting-edge discoveries show
We did it.
black holes are very real.
I thought it was crazy. I said, holy.
But what exactly are they? If we could visit one, what might we see?
I Yeah, welcome back to Unveiling, Astronomy podcast featuring the infinite cosmos. What's up, everybody? Big Germ, what's up, man? Thanks for joining. R.A. George, how you guys doing? Eva, what's going on, guys? Thank you guys for joining. Man, please hit like if you've learned anything. Man, check out my Patreon page. Check out my on my website. You can see what's going on during the month for stargazing, stuff like that. Blah 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 blah. Always fun. But yeah, man, check out becoming a patron. I'm giving away if you become a patron, I have different giveaways with I've got that projection, my astronaut projection. Basically it shoots like these stars in the Milky Way and everything on your ceiling. You can point out different stars, different constellations. It's really cool. And t-shirts, man, I do giveaways all the time. Also doing months free of Star Talk. Star Walk. Really cool apps that you can get. Man, they're super cool to check out the different stars, like the heavens, the orbits of the whole entire world. It's pretty cool, but definitely, man, check out becoming a patron or on my fan base. But yes, please hit like. It helps the channel a million. Can never express that more. Now, what's going on? Another fun news that No, I'm sorry, I'm not getting there yet. But I've got a really cool story for everybody. This one, you guys have to check out. Where did it go? An alien mothership lurking in our solar system could be watching us with tiny probes. The Pentagon officials, suggest and say, coming from the Pentagon. Now, that coming up. But that's pretty cool. So yeah, could an alien mothership be hovering around the solar system, sending out tiny probes to explore planets? According to a Harvard scientist and Pentagon official, it's possible. So I was talking earlier, we were talking about, I will get back right to that, parallax measurements. Now, the parallax angle, how astronomers use angular measurements to compute distances in space is, man, it's really cool. God, it's crazy. And it's all from a basic example. The best way to is stick your thumb out and put it to like a sign or anything it doesn't matter. It could be how far away, across the yard, whatever. And close one eye and then open the other and close the other. And you'll see that there's a difference. And between the object that you're pointing at and the object of your thumb, you create a triangle. Now, the parallax angle is the angle between the Earth at one time of year and the Earth 6 months later, as measured from a nearby star. Astronomers use this angle to find the distance from the Earth to that star. How do scientists measure this angle, and how does this information tell them the distance of the star or to the star? The Earth revolves around the Sun every year, so that every half year, 6 months, it is on the opposite side of the Sun from where it is or was 6 months ago. Because of this, nearby stars will seem to move relative to the distance. And relative to the distant background stars, you can see the effect driving in the country. Nearby road signs seem to move by quickly, but distant buildings, trees, etc. seem to move very slowly. And the Sun doesn't move at all. Well, it wouldn't if the Earth weren't rotating, but you know what I mean. Another illustration, hold a pencil at arm's length and look at it through one eye, then the other. Notice how it shifts position, yet it hasn't actually moved. Your eye models the different positions the Earth is in. First on one side of the Sun, your nose, then the other. Astronomers look at the sky on a specific date and then 6 months later to see how far a nearby star appears to more relative to the background. The angle these astronomers measure the star to move is actually the same angle they would see the Earth move if they could travel to the star. Because the scientists know the distance the Earth has traveled in 6 months, twice the distance to the Sun, they have all the information they need to find the distance to that star. So to do this, the astronomers use a method similar to one you use with your homemade quadrant. Twice the distance to the Sun divided by the distance to the star, which is unknown so far, is equal to the tangent of the parallax angle of the star. So tan of the angle equals 2 AU, or the distance. And AU is the astronomical unit, or the distance between Earth and the Sun, which is 150 million kilometers. Now, yeah. So, oh, hi, Lincoln. Are you want to say hi? So, yeah, 1 AU. Now, oh, Lincoln, what are you doing? Oh, okay. Hi, Lincoln. Thank you. Okay, Lincoln. Thank you. I'm gonna put this on here so that it gives you guys a good it's a drawing to give you let me see there. This will give you a good or somewhat of a diagram to go by. Okay. Good night. Oh, hey, what's up, Kartik? How you doing? Kartik, how you doing? What have you been up to? I just looked down and saw that. Man, what have you been up to? How's everybody doing? Moon, how you doing? What's going on? Thank you guys for joining. If anybody has any questions or anything or wants to call in, definitely do. I love hearing from everybody. So yeah, that is the parallax measurements. Pretty cool. Lincoln, hi Bobby. Do you want to say hi to everybody? Everybody, Lincoln can't stand it. He's saying hi. Hi, Bobbers. Linky. Now in my other news, alien mothership lurking in our solar system could be watching us with tiny probes. Pentagon official suggests. Well, man, this even gets better. It really does. So we got the Pentagon now saying, could an alien mothership be hovering around the solar system, sending out tiny probes to explore planets? According to a Harvard scientist and Pentagon official, it's possible. In a draft paper, the pair said it is feasible an extraterrestrial and extraterrestrial spaceship. Just kidding. I'm not kidding about the story, but an extraterrestrial spaceship could be in our galactic neighborhood, exploring the regions by the means of dandelion seeds, small spacecrafts that can gather and send back information similar to the way humans send out spacecraft to explore planets. A.V. Loeb, an astronomer at Harvard University, and Sean M. Kirkpatrick, director of the Pentagon's All-Domain, established in July 2022 Department of Defense to detect and study objects of interest. Released in a draft. Wow, so... Oh man, that's... yeah. So, there's the physical constraints on unidentified aerial phenomenon. Now, this is a really, really, really long... This is a document from the part of the government. We derive physical constraints on interpretations of high maneuverable, unidentified aerial phenomenon based on standard physics and known forms of matter and radiation. In particular, we show that the friction of UAP with the surrounding air or water is expected to generate a bright optical fireball, ionization shell and tail, implying radio signatures. Now, in 2005, the U.S. Congress asked NASA to find 90% of all near-Earth objects that are larger than 140 meters. The congressional task resulted in the construction of the Pan-STARRS telescope on October. Okay, Lincoln, Jesus, man, you're like beating it. Jesus. On October 19, 2017, the Pan-STARRS Sky Survey flagged an unusual NEO, the interstellar object, Oumuamua, and referenced therein. Unlike solar system asteroids or comets, Oumuamua appeared to have an extreme flat shape and was pushed away from the sun without showing a cometary tail of gas or dust, raising the possibility that was thin and artificially in origin. 3 years later, Pan-STARRS discovered a definitely artificial object named NASA's Rocket Booster 2020 SO, which exhibited similar behavior with an extreme shape, a push by the solar radiation pressure, and no cometary tail because thin walls were made of stainless steel. On March 9, 2017, 6 months before Oumuamua's closest approach to Earth, a meter-sized interstellar meteor collided with Earth. Surprisingly, IM-2 had an identical speed relative to the Sun at large around the Sun was completely different from Oumuamua's, implying the two objects are unrelated. Nevertheless, the coincidences between some orbital parameters of Oumuamua and IM-2 inspires us to consider the Lincoln, what? Oh no. To consider the possibility that an artificial interstellar object could potentially be a parent craft that releases many small probes during its close passage to Earth. An operational construct not too dissimilar from NASA missions. Now, these dandelion seeds could be separated from the parent craft by the tidal gravitational force of the Sun or by maneuvering capability. Lincoln, okay. A small ejection speed of far away could lead to a large deviation from the trajectory of the parent craft near the Sun. The changes would manifest both in arrival time and distance of closest approach to Earth. With proper design, these tiny probes would reach the Earth or solar system planets for exploration, as the parent craft passes by within a fraction of the Earth-Sun separation. Just like Oumuamua did, astronomers would not be able to notice the spray of many probes because they do not reflect enough sunlight for existing survey telescopes to notice them if they are on a 10-centimeter scale of CubeSats or smaller. At a distance d from the Sun and the telescope, objects that are a meter in diameter and reflect a fraction a of sunlight impinging on their surface would yield a flux of optical light of 0.2 d, that's slash 1 AU, well below the detection threshold of even the James Webb. So in contrast, the radar signatures of a meter-class object would be detectable with our deep space radars and space fence, much like IM-2 was out to beyond geosynchronous orbit at an altitude above 36,000 kilometers. Such objects could also become optically detectable as they get close to Earth, especially if they create a fireball as a result of their friction with air. Equipped with a large surface to mass ratio of a parachute, technological dandelion seed could slow down in the Earth's atmosphere to avoid burnup and then pursue their objectives wherever they land. Current radar coverage of the majority of first world countries gives detectability of the high area to mass, or the HAMR, objects down to a few centimeters depending on material, making detectability possible. Within a close range to a star, extraterrestrial technologies probes could use starlight to charge their batteries and liquid water as their fuel. This would explain why they would target the habitable region around stars, where liquid water may exist on the surface of rocky planets with an atmosphere, like the Earth. Habitable planets would be particularly appealing in transit medium probes capable of moving between space, air, and water. From a large distance, Venus, Earth, or Mars would be equally attractive for probes, but upon closer inspection, Earth would show spectral signatures of liquid water through reflection of blue light and vegetation through its red edge that might attract select attention. Seeger, ETAL 2005. Now, what would be the overarching purpose of this journey? In analogy with actual dandelion seeds, the probes could propagate the blueprint of their cinders. As with biological seeds, the raw materials on the planet's surface could also be used by them as nutrients for self-replication or simply scientific exploration. It is important to note that given the timescales associated with the propulsion scheme discussed, it is reasonable to assert that the intention of I'm sorry, my voice just totally I'm sorry. Was that you, Lincoln? Hi, Bobby. That wasn't you. Hi. I know. I love you too, Bobby. Thank you, Linky. Okay, I'm so sorry. Now, not right now, Lincoln. Now, as with biological seeds, I'm sorry. It is important to note that given the timescales associated with the propulsion scheme discussed here, it is unreasonable to assert that the intention of any such probe launched in the far distant past has anything to do with human species. More likely, and similar to NASA's missions, the goal would be scientific and exploratory in nature. Based on the detection rate of interstellar objects, estimated for every interstellar NEO, there are 1,000 solar system NEOs of the same size. Searching for interstellar meteorites among the many more meteorites from the solar system without information about impact velocity is like searching for a needle in a haystack or a needle in a stack of needles. This is why the first interstellar meteor, IMI, confirmed by velocity measurements of the U.S. Space Command, is the target of a fully funded ocean expedition by the Galileo project. Hopefully, by retrieving IMI's fragments within the coming year, we will know whether the extraordinary material strength resulted from being made out of an artificial alloy like stainless steel or materials not yet developed by humans. Are there any functioning extraterrestrial probes near Earth? We don't know. But the Galileo project intends to use the scientific method to explore the possibility, following the 2021 report about unidentified aerial phenomenon. So, the search for UAPs and the characterization of UAP requires bounding the search plan with psychics based on strengths on what we are searching for. This paper aims to constrain one aspect of the UAP hypothesis with parameters that govern the movement and interaction of a UAP with Earth's atmosphere to eliminate or-bound observational uncertainties. Some data collected to date, while arising from multiple sensors, have uncertainties in one or more dimensions, leaving the exploitation of the data with a significant range of interpretations. Now, this inevitably leaves open the debate on what some objects are and whether or not they exhibit truly anomalous behavior. Specifically, if some observed UAP are extraterrestrial origin. There are some practical limits on the interpretation of observed and measured data resulting from physics-based constraints. Now, if you listen to my podcast, you know that I only go off of fact. I usually don't even go into the conspiracy thing, but this was a paper that was sent. This was a part of what part of the CIA. I can put pictures up here for you. PVN 27861. What's up, guys? Moon, you guys still there? Please, if you learn anything or anything, man, hit like, leave comments. I love hearing from you guys. Don't go anywhere. I will be right back. Bye-bye.
Cover doctor visits, prescriptions, emergency care, and more. Healthcare.gov is here for you. Enroll by January 16th.
Seizures before falling into a coma and dying. It later transpired that he had been poisoned by vitamin A from the sled dog's livers. Mawson was alone, but had no choice to continue or face death himself. He eventually made the lonely journey back to his camp, but his bad luck followed him back. He finally arrived to discover that the ship due to take him home had already left just a few hours earlier, forcing him to spend another winter on the ice, with more than enough time to mourn his loss. Despite these horrors, upon returning home, Mawson was awarded
What's up, guys? Welcome back. To No Avail Astronomy Podcast. Now, I was getting into what kind of cover? Yeah, some kind of a CIA paper. I can send pictures. I don't know why my dogs are barking. Yeah. Anyway. In the advent of the story of government saying that there could be what was this? Where did they go? Oh, an alien mothership lurking in our solar system. So, with this paper I was reading, it gets pretty interesting. It really does. Hang on. So you guys can hear more. Oh, no. Now, the extraterrestrial possibility. The academic interest in UAP stems... Shut up, Billy! Stems from their potential non-human technological origin. Extraterrestrial equipment could arrive in two forms. Space trash, similar to the way our own interstellar probes, Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, will appear in 1 billion years, or functional equipment such as autonomous devices equipped with our artificial intelligence or AI, electronic probes employing conventional chemical propulsion and refueling that we currently understand would be a likely choice of travel within a planetary system. Some combination of conventional propulsion, ion propulsion, or light sail propulsion would provide good choices for crossing the tens of thousands of light years that span the scale of the Milky Way galaxy. Such autonomous systems could be designed to survive even if their senders are not able to communicate with them and deposit probes upon arrival to the target planetary systems. It is likely that any functional devices embedded in the Earth's atmosphere are not carrying biological entities because these would not survive the long journey through interstellar space and its harsh conditions, including bombardment by energetic cosmic rays, X-rays and gamma rays, interstellar gas, and dust particles deposit kinetic energy per unit mass that exceeds the output of chemical explosives at the speed of tens of kilometers a second. However, technological devices with AI can be shielded to withstand the hazards of space, repair themselves mechanically, or even reproduce given the resources of habitable planet like Earth. With machine learning capabilities, they can adapt to new circumstances and pursue the goals of their senders without any need for external guidance. As argued by John von Neumann in 1939, the number of such devices could increase exponentially with time if they self-replicate. That was like the Fridas of 1980. Equality enabled by 3D printing and AI technologies, physical artifacts may also carry messages, as envisioned by Ronald Bracewell in 1960, and currently used by NASA. Now, with the propulsion methods, in principle, the fastest devices could be launched by light sails, pushed by powerful light beams up to the speed. Okay, well, we need to talk with Nick B. Hey, what's up? We need to talk. How's it going? Hang on, guys. I need to, I've got something I need to do. So you guys, I'm going to have you guys, I'll be right back.
Biological and geological data that it took 30 years to fully unfold. Though he did later return to Antarctica, Mawson spent much of the rest of his career studying the geology of his native Australia. As professor of geology at the University of Adelaide, he had ample opportunity to consider the geological history of the entire country. And there was perhaps no one more suited to interpret the mysterious rocks that researchers and prospectors were discovering. Across a swathe of the sun-baked continent, there appeared to be almost 1,000 miles of glacial sediments. They were clearly out of place, but they were also incredibly ancient, dating back to the Neoproterozoic period, long before the evolution of animals. Mawson doubtless drew on both his geological and Antarctic experience when he made a remarkable suggestion. Perhaps, he said, the whole of Australia had once been entombed in ice, in some kind of global glaciation. How else could you explain the freezing of a place as hot as Australia, if not by the freezing of the entire world? Mawson's geological and glaciological reasoning were sound, but they failed to account for one thing: continental drift. As the theories of continental drift and subsequently plate tectonics gained ground, they helped geologists to solve the puzzle of these seemingly incongruous deposits. Accepting that the continental masses traveled across the face of the Earth as crustal plates scraped, collided, were destroyed and made anew, permitted places like Australia to become glaciated without the need for a worldwide freeze. During the Neoproterozoic, it turned out, Australia simply lay closer to the poles, and was therefore more likely to experience normal polar conditions. Plate tectonics may have undermined Mawson's conclusions, but that wasn't the end for his ideas.
I used to be trapped in the cycle of bad credit. But then I discovered Self's credit builder account. With Self, I can build my credit and savings at the same time. Here's how it works. I make monthly payments which get reported to the credit bureaus shaping my credit history. Then at the end, I get my savings back, minus interest and fees. Self customers built over $500 million in savings and counting. Click below to get started with Self today.
Get more money in the bank with QuickBooks Money. It's a business bank account that's free to open with no monthly fees or minimum balances. Don't worry about getting overwhelmed with bank fees any longer. Download the app today.
As geologists learned to reconstruct the shuffling of continents through geological time, new sedimentary conundrums began to present themselves. For one, glacial deposits have been found in Greenland and on the Arctic island of Svalbard. On the surface, this is perhaps not surprising, since both of these places experience long polar nights and year-round freezing conditions. But these particular deposits date from around 650 million years ago, when tectonic reconstructions suggest that Svalbard and Greenland lay at tropical latitudes. Ancient ice in Australia may not indicate a global glacier, but ancient ice on Greenland does. But it's not just these two places that hint at an extraordinary Neoproterozoic glaciation. All over the world, geologists use elemental isotopes and local relationships to find the age of their rocks. And they use the alignment of ferromagnetic minerals like hematite and magnetite to the Earth's magnetic field to find the latitudes at which these rocks were formed. Finally, they use clues in the rocks themselves to reconstruct the paleo-environment, and by extension, the paleoclimate at that particular location. Researchers began to find characteristically glacial deposits from the late Neoproterozoic worldwide. They include chaotic, unsorted sediments known as tillites, which are created by the action of glaciers as they churn up existing rock and deposit it. There are also drop stones, large cobbles or pebbles that appear to have been dropped from above into much finer layered sediment. Without having to invoke mysterious rock-slinging deities, these anomalies can be explained by melting icebergs dropping their sediment load far out to sea. Passing glaciers can also polish rock surfaces and leave long, straight scratches known as striations, and lakes that form from glacial meltwater record cumulate, finely layered sediments at their bottoms called varves, which reveal the seasonal ebb and flow of melting waters. All of these features have been found in rocks from the late Neoproterozoic, and most importantly, regardless of the latitude in which they were formed. Dropstones, varves, and tillites from near the equator lead to the inescapable conclusion that there was ice here, and the planet must have looked very different to today. Not only that, but late Neoproterozoic deposits contain some rare and unique rock types that are hard to explain without drastic climatic and oceanographic transformation. Banded iron formations, which disappeared from the planet some 1.5 billion years earlier, now make their reappearance in rocks from 700 million years ago. Their presence implies oceans that were occasionally anoxic, something that would only be possible in the Neoproterozoic waters if something was stopping gases from being exchanged between the atmosphere and ocean. Something, perhaps, like an immense, uninterrupted ice sheet that covered the global ocean like a shell. Finally, in a stroke of remarkable geological synchronicity, researchers have consistently found a single type of rock laid down worldwide directly above the widespread glacial deposits. No one is sure exactly how or why the cap carbonates formed all around the world, all at the same time, but a leading explanation involves the sudden influx of new material from the land surface into an ocean that had become strongly acidic with carbonic acid. Alternatively, the cap carbonates may just represent the moment the oceans breathed again after a long and constricting global freeze. And so, all of these pieces of geological evidence seem to point to the same remarkable conclusion. In the late Neoproterozoic, starting around 750 million years ago, the Earth experienced an intense ice age that saw widespread freezing of the
No,
land,
I can take it right
the ocean.
now.
A global glaciation that caused ice to extend
Tomorrow,
from the poles
there's UPS
right down
right
to the
there.
tropics, perhaps even
I'm going
reaching
to.
the equator. The icehouse world of the tropics, the Earth marked paradise for travel.
Well, that worked out great. Yeah. All right. What else you need anything?
But the period of geological time in which many of these extreme events occur is known as the cryogenic, after the Greek frost. Now that Neoproterozoic rocks have been studied in detail, the individual glaciations
Daniel's here.
rock formations where they were first identified. The Sturtian glaciation is the oldest, occurring between 750 and 660 million years ago. It's followed shortly after by the Minoan Ice Age from 650 to 635 million years ago. Records suggest that a very brief global glaciation followed 570 million years ago, and the final snowball Earth is known as the Baconurian glaciation, and it marks the very end of the Proterozoic period, lasting from 549 to 530
Yeah. You
million
think that
years
you'd
ago.
probably be better driving that?
Yeah, I'll bring it over there.
Well, here, let me. I'll pull it over here and I'll stay right there. Don't move.
Around 2.5 billion years ago, the Earth was pushed into a 300 million year oceanic freeze as a result of the Great Oxidation Event, and the atmospheric changes that followed. But more than 1,500 million years have passed since then, and the Neoproterozoic Earth is a very different, complex, cooperative, and the stakes are higher than ever. Just how hard will it be to survive on a cryogenian Earth? system on a slingshot course towards the sun. Flung on this fateful trajectory millions of years before from its home in the distant Kuiper belt, it has swung and whisked around its star nearly 1 million times. But with a lonely comet's days,
Don't you think you like
numbered,
driving a truck
this
better?
may well be its last
Yeah.
stellar tour. With every approach,
Okay.
the sun's heat evaporates
Yeah,
some of
you
its
need
space
that.
mantle, sending
I
it
hate to
streaming
have
behind
that.
in a glorious
Thank you.
rainbow-lit
All right.
and the once
Yeah,
magnificent
I
icy
can get her.
asteroid is
Thank
now
you.
but a shadow of its former self. Nevertheless,
All right.
flies. Sailed
I
past
love
Neptune
you.
and Uranus, cold
Yeah.
giants lurking in the dark. Girdled by rings and looming Jupiter, its ungrouping moon.
I think it'll be better.
But with the assist of the relative clutter of the rocky asteroid belt, the sun's warmth begins to grow, and the comet begins to glow. When it goes into the inner solar system and past the already dry and dusty Mars. It's still 700 million years before humanity will evolve to recognize its reddish glow in the night sky. But Mars has already lost its life-giving atmosphere and oceans to the unforgiving.
All right, everybody, what's going on? Sanctuary of the Divinity. We need to talk. What's going on? All right, guys, I'm back. Now I'm reading this physical constraints of unidentified aerial phenomena. Now this is here. I'll take a picture of this and I will put it over here for you, for your visual eyes as well, just in case you want to read it. If not, I will read it to you. It's got all the references. There's all the references. Okay. Now, I'm going to try to do this so that... Boom. Here is this. Done. And then I'll put... let me see. This will have all the references on it. So everybody can read that. Now, going back to that. Sorry, my dad hit me up and I had to do some stuff for him. Okay. Anyway, now I was on page... Yeah. Okay, the extraterrestrial possibility. Now, the academic interest... Let me turn this thing down so that you guys can... turn it down a little bit, maybe. Okay. Alright. Thank you for hitting like. I appreciate it. If you like this channel, please hit like and follow if you have not followed. All of you guys are awesome, man. You don't know how much I appreciate every one of you. Alright, now, the extra testicle possibility. I'm kidding. The extraterrestrial. Now, the academic interest in UAP stems from their potential non-human technological origin. Extraterrestrials' equipment could arrive in two forms. Space trash, I've already read this, haven't I? Oh, I'm going to reread it anyway. Similar to the way our interstellar probes, Voyager 1 and 2 and 3 work. Okay. It is likely that any functioning devices embedded at the Earth's atmosphere are not carrying biological entities because these would not survive the long journey through interstellar space. Propulsion methods, that's where I was at. In principle, the fastest devices could be launched by light sails, pushed by powerful light beams up to the speed of light. Natural processes such as interstellar explosions or gravitational slingshots near black hole pairs could launch objects to similar speeds. However, it would be difficult for relative payloads to slow down below the escape speed of Earth, which is 10 for this, without having around the same facilities that generate their high initial speeds. A better suited propulsion technique that was used in all planetary space missions from Earth is chemical rockets. Now, since rockets carry their fuel, they can navigate to a desired planet and slow down near it. Alternatively, it may be possible to use one of the above methods to travel and through a planetary system, deploying interplanetary probes using conventional chemical propulsions. For a rocket of total mass m and exhaust speed of the bladed gas relative to the rocket momentum, conservation implies MIV equals MV EXH. Now, where an overdot denotes a partial time derivative. The best solution to the rocket equation implies that for a reasonable fuel to payload mass ratio, the final speed be an order of magnitude larger than the exhaust speed. For typical chemical propulsions with this tyranny of the rocket equation explains why all human-made spacecraft reach a speed limit to the tens of kilometers. Interestingly, this speed is comparable to the escape speed from the Earth's orbit around the Sun, making it possible for humanity to launch interstellar probes which take advantage of the motion of Earth around the Sun. At its contrast, the nearest the star Proxima Centauri. In summary, chemical propulsion allows escape from the habitable zone of sun-like stars and enables slowing down near a destination. Now, devices which need to refuel would favor a habitable planet where liquid water or combustible organic fuel are available. The exhaust velocity of hydrogen-oxygen for rocket fuel is about 4.5 kilometers a second. And so pure liquid hydrogen or oxygen is insufficient to slow down the characteristic free-fall speed of over 40 kilometers a second from interstellar space to the habitable zone around the Sun, unless the fuel mass is many as hydrocarbons, would result in other chemical byproducts at the craft's exhaust, which would then have distinct spectral signatures. This implies that chemical propulsion, while sufficient to escape the habitable zone using Earth's motion around the Sun, is insufficient to slow down from interstellar space to the planet's surface in the habitable zone without the basis of the fuel would also require cold temperatures. Between hot exhaust, steam, or other chemical byproducts, and cold storage, 20 K for hydrogen, this gives rise to additional signatures for characterization. Planets can be identified from a distance as they transit their star or through direct imaging. Once an Earth-like planet is targeted, an interstellar device can plunge into the atmosphere. In principle, a multitude of tiny devices can be released from a mothership that passes near Earth. A probe would cross twice the distance of the Sun from the Milky Way center within a time of 0.5 GYRs. The fraction of all Sun-like stars that host Earth-like planets in their habitable zone is in the range of 3 to 100%. So this implies that self-replicating probes could reach 10 to 10 to the power habitable planets around the Sun-like stars in less than 1 billion years. Since most stars formed more than 1 billion years before the Sun, it is possible that other technological civilizations predated ours by the amount of time needed for the devices to reach Earth. Here we can use time as another constraint. In the propulsion scheme, where am I? Is everybody still there? How's everybody doing? Where am I at? Alright. Where was I? Now, a detailed statistical analysis of EZEL showed that the inferred abundance of probes is distinctly different in case of objects being targeted towards particular regions of the galaxy, specifically habitable zones containing planets. Oumuamua was detected at a distance of 0.2 AU from Earth, and it passed through the habitable zone of our solar system. The estimated total number of Oumuamua-like objects would then fall by a factor of 2 to 10. So in the case of targeted probes compared to probes on random trajectories, the interstellar meteor IM-1 had an estimated diameter of 0.45 meters and velocity of 60 kilometers a second, but it was detectable when it burned up within the atmosphere of the Earth. The estimated detection rate for meteor-sized interstellar meteors is at least 0.1 year, so resulting in a local density estimate of the objects with the properties of IM-1 were targeted toward the... Hey everybody! I know I didn't... Please don't... No. Wow, the doors are locked on QT. It's closed. Please use other doors. God. How's everybody doing? I can't believe I just had that conversation. Ah, yeah. Oh man. So, anyway. I'm sorry everybody. I gotta get to this. I'll let you guys listen to this.
Solar wind. Only a little water remains, frozen at the red planet's poles. Closer still to the sun and the melting comet's days, numbered. The Earth's single gigantic moon is its penultimate flyby, and as the Earth itself grows larger in the comet's surface, and the sun's heat eats away at the comet's core, two frozen bodies glow as brightly as one another. On one side of the sky, an icy asteroid is about to meet its end, and on the Earth, an entire icy planet. There is no end in sight. It sits squarely in the warmth of the sun's habitable zone, and yet not a drop of liquid water is to be seen. In the clear night skies above this snowball Earth, the comet disintegrates and evaporates into a superheated vapor. But on the planet's surface, the big freeze continues on. A crushing global winter with no easy way out. From the air, the blindingly sunlit dayside is cast into sharp relief by its shadowed night, separated by a smooth terminus uninterrupted by either mountain or valley. But the planet's night side is not complete. It reflects the star and moonlight, giving an entire hemisphere an eerie grey glow. Yet it's almost impossible to see the planet spin as the featureless globe slides beneath its shadows. Time on Earth during the cryogenian is just as undifferentiated as its geography.
Or worse.
Seasons pass, winter to summer, but with no visible change on the surface. All remains white. Years, decades, and millennia pass through cycles of solar activity and subtle changes in Earth's orbit and spin. But still, there is no visible change on the surface. It's easy to lose track of time, and before you know it, 90 million years have passed. on the surface that it's possible to differentiate between icy land and icy ocean. The sea ice appears as an endless, smooth expanse, interrupted only by larger icebergs trapped and frozen in place. But approaching the hidden shoreline, the ice cracks and heaves in chaotic, slow motion, the result of tidal forces bulging the still liquid ocean beneath many meters of ice. There are long, flat, white coastal plains that then rise to a rolling, rocky landscape. But all is smoothed and softened by the indiscriminating blanket of snow and ice. Only occasionally is a sharp, rocky ridge or peak visible, blown free of snow and ice by the unforgiving wind. Indeed, wind is likely the only weather that this frozen ball will experience. With temperatures at the equator as low as those on modern-day Antarctica, there's no spare energy in the atmosphere for brewing storms or rain clouds. Ice covers every surface, becoming a barrier to evaporation and making it extremely difficult to pump water vapor into the air. Without clouds through the night, there's little retention of heat close to the surface, and at night especially, the temperatures plummet even further. It is unfathomably dry and cold, but still, the wind blows. From warmer dayside to colder nightside, or from extremely cold mountaintops to only very cold shorelines, the wind blows, uninterrupted across the featureless surface. It whips loose snow and ice crystals into a sparkling ice mist, and rivers of powder blue across the ground. It would be quite beautiful if it weren't so deadly. For the surface is most certainly inhospitable to life. Atop the snow and ice, there is none of the water that every life form needs to survive. And since snow and ice cover the entire globe, there would seem to be nowhere left for Earth's fragile inhabitants to cling on. And yet, cling on they do. The ever-innovative biological metabolism is capable of endless variations. By 750 million years ago, bacteria, algae, and the unicellular ancestors of animals had already adapted to inhabit almost every corner of the oceans and inland waters, beginning to creep their way onto land from the shores too. So when the Earth froze over, life may have lost most of its territory, but it was able to persist in whatever stronghold, whatever refugia it might find. While on the grand global scale the Earth is featurelessly frozen, there will always be some fine-scale variation, some tiny cracks in the facade that life can exploit. Beneath the thick oceanic ice shelf, the oceans are not frozen to the bottom. They might be pitch black, they might be anoxic and stagnant, but there are microbes that can still eke out an existence on such meager rations. Life's ancestral refuge still exists at the very bottom of these stagnant oceans too. Hydrothermal vents pump warm, mineral-rich water out onto the sea floor, and they are colonized, get all they need from the minerals that build the underwater volcanic chimneys. There are opportunities for the photosynthesizers too, even though the freezing temperatures at the sunlit surface are at first grossly incompatible with these organisms' need for light. But again, cracks in the facade leave space for algae to scrape by. Where the sea ice has heaved and cracked and changed its shape a million times, pockets of water could become trapped close enough to the surface to receive a faint, life-giving glimmer. Similarly, as the days and seasons come and go, some ice inevitably thins and cracks when exposed to the unforgiving glare of the midday or midsummer sun, producing small areas of translucency or even open water. It would freeze again when the sun sets or winter rolls around, but life has taken its chance and can sleep out the coldest times in sun-fattened dormancy. Microbial life is even able to build its own habitable microcosm on the surface of the ice, creating and expanding dark, water-filled pits like Swiss cheese. Known as cryoconites, These vertical holes begin to form when the sunlight seizes up the dark color of dust grains trapped within the ice, warming it up more than its surroundings, which allows it to melt the ice around it. As the hole expands, it captures more of the warming dust, and it's colonized by dark-colored snow algae that accelerates the warming with melting effect. Indeed, even when the world is at its coldest, these cryoconites are proof that life not only finds a way.
Right, now, if everybody's still there. So, in addition to the thermal shock and associated optimal signatures of a high velocity, highly maneuvering object, there is also an ionization and associated radio frequency signature from such an object moving through the atmosphere. Hawaii UFO Roundup. Really? Wow. So studies into the supersonic and hypersonic vehicles provide a good base for comparison. While the ionization density depends on the altitude, shape, material, and velocity of the object in motion, some limits can be derived on when a signature would be detected, implying a limit to the object's motion prior to the fireball threshold. In particular, ionization at high velocities leads to an increase in radar reflectivity along the ionization edge of the object and along the ionization trail. Both give rise to enhanced radio frequency. Fuck my fucking God. What a bitch. You're a fucking bitch. Fuck you, Katie. Piece of fuck shit. Go die somewhere. Please. Fucking moron. Fuck your stupid side. I'll show you a side. A B. You'll never fucking... God damn, you're a trashy piece of shit. Okay, everybody. I gotta get off. Well, Mikey, what's up? Alright, so, yeah, this a signature would be detected implying a limit to the object's motion prior to the fireball threshold. In particular, ionization at high velocities leads to an increase in radar reflectivity along the ionization edge of the object and along the ionization trail. Both give rise to enhanced radio frequency reflection for frequency below the cutoff frequency. So, whether or not we have an alien mothership lurking in our solar system, and whether that paper is something that is wow. It's pretty cool. Pretty cool weather. I mean, pretty cool weather. It's pretty cool news. Well, I appreciate everybody. Man, if you want, definitely anybody call in or anything you need. But if not, until then, another wonderful episode of the Infinite Cosmos featuring the Noah Fail Astronomy. Man, you guys have a wonderful day, and please join me again on another episode. Check out my Patreon page to get more detailed podcasts. I do all my live shows, but if you want to check out my my in-depth podcast, become a patron, or on my fan base page, check out my website for upcoming events, in the sky, and other things coming up. So definitely check out my page, become a patron, and win some stuff. I got some shirts and some awesome. I got some awesome little these little. Well, what am I trying to say? Like a little astronauts that project. I can't think that project stuff. I got all kinds of stuff, but anyway. I'm getting it all together and more. Definitely become a Patreon, and man, I will see you guys soon. You guys have a good one.